The following program is brought to you by Caltech.
My name is Ralph Nuzzo. I'm happy to welcome the audience and our web guests to a webinar sponsored by the Light Matter Interactions EFRC here at Caltech today. I serve as the Associate Director of the LMI EFRC, and well, I should say a little bit about what the LMI EFRC is. This is a multi-investigator research program funded by the Department of Energy, which is meant to foster forms of collaboration and progress in research that basically exceed capabilities that might be done by single investigators. We seek to bring together a body of science that would serve as a national resource for the science of optical materials, in particular with respect to how they might be utilized to provide new capacities and competencies for solar energy conversion. And during the next 2 hours, we're going to have a series of 3 talks that'll be presented by investigators of the EFRC and that will show you some of the real highlights of the science that's being done within this program. And I want to welcome our web-based guests especially. And there's a couple of points that I want to let you know about that we encourage your participation throughout this talk. And there's an important point to understand about that your participation can come in the form of comments and questions, but and you can utilize your capabilities to do that anytime using the chat function on Ustream. But important point to note is that if you wish to do that, even though you do not need to be logged in order to observe the presentations, the chat function is only enabled if you are in fact logged in. So we would encourage you to do that and really hope that you will be an active participant in the lecture today. So what I'd like to do is actually hand this off to the very capable person who makes absolutely everything work in the EFRC, Dr. Kari Hoffman. Thank you.
Okay, well, welcome. Today I'm going to introduce our first speaker, Dr. Harry Atwater. He's the director of the LMI EFRC and the Howard Hughes Professor of Applied Physics and Materials Science at Caltech. Harry Atwater currently serves as both the director of the EFRC and of the Resnick Institute for Science, Energy, and Sustainability at Caltech. It's the largest endowed research program here. His scientific interests have 2 themes, photovoltaics and solar energy. His group has created new high-efficiency solar cell designs, developed principles for light trapping, and he's an early pioneer in the field of plasmonics. He actually gave the name to the field of plasmonics in 2001. He's authored or co-authored more than 400 publications, cited in aggregate greater than 18,000 times. His group's advances in the solar energy and plasmonics field have been reported in numerous publications, including Scientific American, Science, Nature Materials, Nature Photonics, and Advanced Materials. Harry is a founder and chief technical advisor for 2 venture-backed photovoltaic companies, including Calyx Solar Energy in Pasadena, California, and Alta Devices in Santa Clara, California. He is an MRS fellow and has been honored by numerous awards, including most recently a fellowship from the Royal Netherlands Academy of Arts and Sciences in 2013 and the ENI Award in Renewable and Non-Conventional Energy in 2012. And today he's going to be telling us about photonic design principles for ultra-high efficiency photovoltaics.
All right, so I wanted to share with you this morning some design approaches, photonic design approaches for ultra-high efficiency photovoltaics. And in order to do that, we're going to frame this in terms of a thermodynamic approach to photovoltaic efficiency, and that will lead naturally into a discussion of several opportunities, including light trapping, photon recycling, control of the angle of emission of photons from photovoltaic cells, and also addressing probably what is the biggest opportunity, which is thermalization in photovoltaics. And I want to acknowledge a group of collaborators through the EFRC who have made this be a very rich and active and interesting research program, as Carrie and Ralph both in their introductions indicated, this is a very rich and interactive collaboration. And so we have a number of collaborators at Caltech and in Berkeley, and I'll also acknowledge a longstanding collaboration with Albert Pullman from the Netherlands, and also valuable inputs from some of the spin-off companies that have come out of the laboratory and have worked with the EFRC. So one of the things I wanted to do to start with is to frame the discussion about efficiency in terms of some of the recent dramatic changes in the photovoltaics industry. And the most notable aspect over the last couple of years is that the PV technology is in real time rapidly declining in cost. And this shows the historical so-called learning curve, where if we look at the cost per watt of photovoltaic modules as a function of the aggregate output of photovoltaic modules. And you can see since the inception of the photovoltaics industry, it's been following this 80% progress curve, essentially. That is, when the volume of modules doubles, the price declines by 20%. And so essentially through several decades in cost per watt of modules, this price has, this curve has been followed. However, what we've seen in the last couple of years is that there's been a dramatic price change in which photovoltaic modules have fallen off the learning curve, essentially. So the cost per watt now is well below $1 a watt. In fact, at the moment, the prices are in the range of 70, 80 cents a watt, and there are credible forecasts that indicate that photovoltaic modules will reach below 50 cents a watt, which was the Department of Energy Sunshot target goal for modules only a couple of years ago, by 2015. And if this occurs, that means that it's going to be very, very challenging for incipient and insurgent technologies to challenge the mainstream silicon photovoltaics technology in cost per watt. So what are the ways that an innovative technology could do so? If we frame this in terms of the overall requirements for photovoltaics, the most important requirement at the terawatt scale is to compete directly with large-scale electricity production by any means. And so that means that the levelized cost of electricity has to be less than the cost of the lowest cost fossil fuel. That's a very challenging objective, particularly nowadays when we have shale gas abundantly available in the United States and similar shale gas discoveries occurring all over the world, which are lowering the cost of fossil fuels. Likewise, we need to have the energy return on investment for photovoltaics at very large-scale deployment be less than that for the lowest cost fossil fuel. And so that's going to suggest that we're going to need to have the entire system cost for photovoltaic installations be less than $1 a watt in order to achieve those price goals relative to fossil fuels, and that the energy inputs required for photovoltaic module and system production should be relatively low compared to other energy inputs of other energy sources. So one question we might ask is, does this mean we should be aiming for high efficiency or low cost? And historically, the photovoltaics industry framed its strategy for different PV technologies around this dichotomy. And what's been recognized in the last couple of years is that this is a false dichotomy, and that in fact we should be aiming for high efficiency and low cost. And in order to do that, that's going to require cell efficiencies in excess of 20%. That's just a reality of the fact that the competitive technology, crystalline silicon, is going to have its median cell efficiency and module efficiency in the whole manufacturing supply stack of the PV industry, reaching up into that range. And that the entire cost of modules has to be low at scale in the range of 40 cents a watt or less. And that's a very challenging situation. That is going to define a strategy that is guiding our work, which is to work with the highest quality possible materials, to work with single crystal materials. They need not be single crystal, but they should have the properties, electronic and optical properties of single crystal materials. And to combine that with light management to go to higher efficiencies than is possible using conventional PV technology like crystalline silicon. Also, what we're going to find is that in single crystal materials, historically the cost has been limited by the cost of wafers, and in order to overcome that cost barrier, it's going to be of particular interest to look at waferless technologies, where it's possible to achieve single crystal performance without consuming a thicker, bulky, and relatively expensive wafer as a function in the cell fabrication. So if we think about any photovoltaic technology, you can think about partitioning the development of that technology into 3 eras. There's a materials development era during which the basic properties of materials are defined and developed. The crystal growth and purification of materials occurs in this phase, and we finally make materials that are of high enough quality to be usable in photovoltaics. And then there's a second era that usually ensues in which the electrical engineers take over from the material scientists and the physicists, and they develop cell designs that efficiently collect carriers that take advantage of the high collection efficiency materials that have been created by making high quality materials. And the electric fields, the internal fields, are optimized to do that, and the overall cell design is designed for efficient carrier collection. But there's a third era in the development of photovoltaic technology that is really just emerging at the moment for many technologies, the ones that have quite mature device technologies particularly, as a big opportunity, and that's photon management. And photon management offers us the chance to go beyond not only current records, but to go beyond the one-sun single junction Shockley-Queisser limit for many different PV technologies. And photon management could include elements such as light trapping, the control of emission angle of radiated photons and scattered photons from cells, and of course spectrum splitting and reduction of the thermalization losses by use of multiple absorbers in a cell. And if we think about the efficiency of a photovoltaic device, the efficiency can be understood in terms of the balance between the absorption and emission from the cell. If we think about using very high quality materials such that all of the non-radiative centers are removed by good crystal growth and purification of the material, such that the photovoltaic material is in the radiative limit, where the primary recombination process, or essentially the only recombination process of significance, is radiative emission, then as was done originally by Shockley and Queisser in their detailed balance picture, the absorption of sunlight that we can accomplish in a thin film cell or a crystalline cell of this kind is limited or dictated by the detailed balance between the absorption and emission of sunlight. Now, if we add to this detailed balance flux picture, and in fact the Shockley-Queisser model really is just a flux balance picture, if we add to this picture now an energy diagram depicting simply in schematic terms a valence and a conduction band for a semiconductor, we can see we're photoexciting carriers from the valence band to the conduction band by photoabsorption and balancing that by radiative emission by radiative recombination from band to band. And if you looked at this picture naively, you might think, well, the open circuit voltage that I could achieve, the maximum voltage I could achieve, would actually be equal to the band gap energy. And Shockley and Queisser showed that that would be possible in the limit of going all the way to 0 temperature in the radiative limit. And of course, since we don't operate cells at 0 Kelvin, then the practical limits are actually defined by a thermodynamic Helmholtz free energy balance, in which we can separate the internal energy that's created by charge separation of electron-hole pairs across the band gap, and entropic terms that actually reduce the free energy of charge separation and therefore the operating and open circuit voltages of the cell by several important entropic features in the operation of the cell. And so what we can see is that upon more detailed analysis is that there are increases in entropy of photons as they are absorbed and emitted from a cell by changes in the distribution of directions. So for example, light coming in from the sun is actually, on a bright sunny day, is coming in from a very collimated source. And in fact, the collimation is almost as good as the collimation coming from a laser or a very like a spotlight. And as light is radiated by spontaneous emission, that light is radiated isotropically both within the cell and then as it's scattered out. And that represents an increase in entropy by the increase in the number of directions that define the number of modes that can be accessed by the radiatively emitted photons. There's also essentially an entropy, one can frame this in terms of an entropy penalty due to incomplete light trapping. And also, if the radiative efficiency of the cell is less than unity, if it's not completely in the radiative limit, then that produces a further loss. And these all translate into losses in the open circuit and then the operating voltage of the solar cell. So this is not only a sort of simple theoretical picture, it's also borne out quite widely in reality. And this plot shows, it's a nice plot from Richard King, my friend Richard King at Spectrolab, that shows the open circuit voltage of a solar cell here depicted with experimental points for a large number of solar cells in the compound semiconductor family between 0.6 and 2 eV. And you can see that the offset between the open circuit voltage and the band gap is almost a constant of about 400 or 500 millivolts. And this set of data here depicts the subtraction of the open circuit voltage from the band gap. And you can see that sum of entropic terms that I was speaking about on the previous slide is in fact limiting the open circuit voltage to be less than the band gap energy by about this number, almost independent. These are all high quality cells and quite pervasively across the range of cell band gaps. So if we think about this analysis in terms of opportunities for increasing the efficiency of photovoltaic devices, then we can think about this opportunity in terms of a series of bars that are here due to increase in efficiency by better photon management through light trapping, by control of the angle of scattered and radiatively emitted photons from cells. And also here, of course, the big bar is due to the mitigation of thermalization losses. There are some other features up here that separate current record and real-world efficiencies from the absolute limits of photovoltaic efficiency that have to do with some more exotic approaches. For example, the fact that typical PV materials and media are obey time reversal symmetry, and therefore they transmit photons in both directions with the same transmittance. If we could make truly one-way materials, and in fact there are some emerging ideas in the metamaterials and nanophotonics arena to make materials that disrupt this time reversal symmetry, then one might be able to possibly recoup an additional efficiency element. So using structures that we can fabricate and integrate into photovoltaic cells, one could conceivably then mitigate the losses due to increase in emission angle and losses due to incomplete light trapping by nanophotonic and microphotonic structures that we integrate directly onto the surface of a thin film photovoltaic cell. And then, of course, the energy losses due to thermalization of photons could best be managed by thinking about making multi-absorber cells where we now, instead of, as in conventional multi-junctions where we have 2 or 3 absorbers, if we now proliferate the number of individual absorber layers in a cell and are able to split the solar spectrum such that a spectral band that's well matched to each absorber and its optimal absorption coefficient is able to distribute the entire solar spectrum among this array of optically in parallel cells, then much higher efficiencies could be achieved. And of course, this requires a photonic design of this spectrum splitting structure as a critical element for success. So let's think about light trapping first. Light trapping has been thought about in models developed by Professor Eli Jablonovich, who will share the podium here shortly. And about 25 years ago, Eli developed, in the context of ray optic light trapping, a statistical ray optics approach that showed that there could be an increase in the internal intensity and the absorption in a wafer or sort of slab-based absorber, like a wafer-based solar cell, by now not making this absorption occur at a planar surface, where by Snell's law we can excite radiating modes that lie within a internal absorption or by reversal and emission cone, But by producing scattering structures on the surface, if we can now scatter light obliquely out of this internal absorption or emission cone, we can fully populate the modes, giving rise to an increase in the internal intensity by a factor of 4 times the refractive index squared. So then for a fixed photovoltaic absorber thickness, one can think about increasing the photocurrent. Or one can think, if one has a target photocurrent in mind for a solar cell, one could then design, in principle using light trapping techniques, a thinner solar cell to achieve the same target photocurrent. And if we think then about the current, in the current technology that focuses on thin film cells, where the entire cell thickness is of the order of a wavelength thick, then we can no longer use ray optic models to describe the picture, and we need to adapt this statistical ray optics picture to a wave optics picture that takes into account the coherent excitation of modes in cells where the entire thickness is comparable to the wavelength. And then the appropriate description of the internal energy density is then in terms of the mode density times the energy per photon excited in the mode times the modal occupancy. And so that leads naturally to the notion that this local density of optical states, or often termed local density of photonic modes, is a key quantity in determining what the internal intensity and therefore the absorption in such a wave optic wavelength scale thickness solar cell could be. And this is a rather complicated plot here that depicts a number of motifs for thin film solar cells, including just a thin film here schematically here of silicon with a metallic back reflector, silicon clad with 2 metal layers in a slot format, a silicon absorber clad by dielectric materials, a photonic crystal, and then finally a photovoltaic absorber here coupled inside an optical antenna. And if we now compute the optical local density of optical states and compare that to that of a bulk material, we can find, for example, in a thin film of silicon that local density of optical states is always less than that of the corresponding bulk. That makes sense. It says that the number of modes that can be supported in a thin film is less than the number of modes in a bulk material. However, if we do something as simple as put a metallic back reflector or make a dielectric slot structure here with a high dielectric constant, low dielectric constant, high dielectric constant, or make a photonic crystal, all of these have the characteristics that for certain wavelength regimes and thicknesses, the photonic density of modes can be dramatically higher than it is in the bulk of that semiconductor material. So these offer opportunities for making wavelength scale structures that have more absorption per volume than their corresponding bulk materials. And here's a couple of examples of structures here shown, illustrated with a organic polythiophene semiconductor absorber layer in which high dielectric constant cladding layers can allow one to exceed the ray optic light trapping limit. And here an array of optical antennas clad around the absorber layer accomplishes the same thing. In fact, we can also think about using metallic structures to do, and there's been a great deal of thinking and progress and experimentation on so-called plasmonic light trapping, in which metal dielectric structures that support localized and propagating plasmons can act as mode converters, converting incident sunlight into waveguide modes in a thin film solar cell, whose thickness might be in the optically thin regime without such a structure. And here's an example of such a structure. This is from the work of EFRC researcher Vivian Ferry, also done in collaboration with the group of the Amolf Institute in the Netherlands, on the fabrication of nanostructured plasmonic back reflectors that act as mode converters. And using a soft imprint patterning technique, it's possible to print these over large areas. And in this case, the photoabsorber is a PIN amorphous silicon solar cell, which is conformally grown on top of this plasmonic back reflector. And what Vivian found was that, in fact, one can achieve substantial increases in the photocurrent over a either a flat back reflector or even a randomly textured back reflector, which for many years was the industry standard for back reflectors in thin film solar cells. So this simply shows that by optimal design of these plasmonic back reflectors, it's possible to achieve substantial increases in photocurrent that are manifest in the spectral response in terms of an increase in the blue response and the red response due to the reduced surface reflection and the excitation of these in-plane block modes and localized modes that enhance the red response over that of a thin film cell otherwise. You can see this quite simply in terms of the modes that are excited and a full wave simulation shows that the amount of power that's usefully absorbed in the semiconductor absorber layer is considerably higher at different regions throughout the visible regime than for a randomly textured back reflector. And this kind of full wave optical analysis allows us to understand the physics. For example, we see parasitic absorption in the metal in these sharp asperities on a randomly textured back reflector. If we want to apply these same light trapping techniques to a crystalline material, we can think about a motif like this. It's a very high aspect ratio microwire cell in which each cell acts as an individual photodiode with a PN junction. These wires are made by a growth process, vapor liquid solid growth process, and they grow by a catalyzed, selectively catalyzed growth process by vapor liquid solid growth. Large uniform arrays of wires can be fabricated over typical areas that are comparable to typical photovoltaic cells, and by a series of processing steps that mirrors the processing steps that are used in conventional photovoltaic cells for silicon fabrication, it's possible to make diffused PN junctions, coat them with anti-reflection and passivation layers that give rise to efficient photocarrier collection, and then finally to encapsulate the whole structure in a polymer with a transparent metal front contact that is and such that the cell is peeled off the substrate, making a flexible thin film cell. So this is an approach for making an extremely efficient light trapping structure that is also at the same time a waferless thin film silicon cell. In order to achieve efficiencies that are well in excess of silicon photovoltaic efficiencies, it's going to be necessary to think about going beyond silicon as an absorber material. And we've been thinking about how this might be done by integrating compound semiconductor materials, compound semiconductors in the 3,5 compound family, either by conformal growth or by selective epitaxial growth integrated with these silicon microwires. And by proper combination of the band gaps of the top and bottom cell materials, it's possible to substantially increase the efficiencies. In this conformal growth approach, in order to achieve high quality material, one would need to achieve a lattice match structure. That would require a constraint on the materials. For the selective growth approaches, it's possible to think about making lattice mismatched designs. So for example, this illustrates the conformal growth here, a conformal growth of gallium phosphide on silicon microwires, here done at Lawrence Berkeley Laboratories. And one can also use the compound semiconductor growth methods to selectively grow compound semiconductor materials in a way such that the lattice mismatch defects can be relieved in the selective epitaxy. And indeed, the other thing that's striking is that the photocurrents in the photoabsorption and photocurrents achievable in this kind of structure are actually matched between the silicon and compound semiconductor layers. Ultimately, though, we want to work with the highest possible quality materials, and I know Eli will say a little bit more about this, and that involves use of single crystal materials, for example, of 3,5 compounds like gallium arsenide. And in order to efficiently leverage the ability to make single crystal cells and do that in a cost-efficient manner, we utilize a process in which cells are peeled off their growth substrates by an epitaxial lift-off process, very similar to the way a sticky note would be peeled off a pad of sticky notes. But in this case, the thin note here is a single crystal film of gallium arsenide that can be fashioned and processed into a solar cell. And that solar cell is made of a material that has very high radiative efficiency, and by virtue of the lifted off cell design, has a highly reflecting back reflector. And this is a great prescription for internal photon recycling, which has the same effect as increasing the optical concentration by the light trapping techniques that I described earlier, but doesn't necessarily require a nanoscale texturing to achieve this enhancement. It's due to the internal radiative emission that causes photons to be recycled between electron hole pairs extensively in this high radiative efficiency material. And that allows one to make, and this is a series of records that have been set by Alta Devices for open circuit voltage and efficiency in these thin film gallium arsenide cells. This depicts the current voltage characteristics of the record single junction cell at 28.8%. That's also led to the development of record efficiency modules, and this just shows some of the things that one can make with these flexible thin film cells, like a mat to charge your computer, or for example, something that you can integrate on the back of your mobile phone. So it's possible to think about further increasing the efficiency of these high radiative efficiency cells by building microstructures that collimate the light coming in. And this shows schematically two kinds of structures that look like microscale versions of conventional concentrators that have the effect by photon collimation of reducing the dark current emitted from a solar cell. And because the voltage scales as the log of the photocurrent over the dark current, then it's possible by simply reducing the dark current to the minimum necessary to create the full absorption in the cell, and no more, to increase the open circuit voltage. And we've begun experimenting with ways that this could be done by microscale fabrication, and this depicts the fabrication of microphotonic collimators made by a prototypical fabrication but with 2-photon lithography. And this leads to collimation. You can see light coming out at various heights above the surface of the collimator, which is quite highly collimated compared to a bare hole aperture in a thin film. And this collimation of the light leads for high radiative efficiency to increases in the open circuit voltage and efficiency of the cell. If the internal radiative efficiency could be 1 for all solar intensities, then this would be a very high efficiency exceeding 40%. We can't do that in practice because, for example, Auger recombination limits the radiative efficiency at high intensities. But indeed, efficiencies in the 30s% for single junction high radiative efficiency cells seem to be possible using this approach. Finally, before finishing, I'll just mention that the big opportunity for increase in efficiency is to mitigate the thermalization losses. Conventionally, this has been done using tandem multi-junction solar cells, and that with a number of absorbers which are constrained by the need to do epitaxial growth of all of the layers in a optically in series stack here. In fact, these cells are almost always in monolithic form, electrically in series. As a result, that offers some constraints on the power conversion efficiency of a cell compared to an optically and electrically in parallel design in which, as I mentioned earlier, light is split into narrow spectral bands impinging on each cell. So this means that to think about a photovoltaic module, it requires essentially a change, a sort of cultural change in the way we make things. Instead of making modules as assembled with arrays of monolithic cells, we're talking about building something that's more like a complex optoelectronic integrated circuit. Using some of the techniques, for example, and I know John Rogers will talk in a moment about some of these, using the microscale liftoff techniques to make arrays of large numbers of cells all on one substrate. So this requires sort of a sociological and cultural change in the photovoltaics technology, in addition to looking at some of the scientific opportunities. And indeed, complex optoelectronic integrated circuits that are commodities are in front of us every day in the form of our flat screen displays on our laptops and projectors and so forth. And if we make now cells that consist of not single or 2 or 3 or even 4 absorbers, but say in the range of 6 to 20 absorbers, one can now define a series of spectral bands that creates, particularly combined with solar concentration, a substantial increase in the achievable photovoltaic efficiency for realistic realistic quality materials. And so going, say, from 3 or 4 junctions to maybe 8 junctions can yield the same increase in efficiency as is possible by solar concentration, going from 1 sun to 500 to 1,000 suns. So I've covered a variety of approaches in which photonic design can yield a new era of high efficiency photovoltaics, and this will require careful analysis and design of light trapping structures in which we design the local density of optical states. And we want to use high internal radiative efficiency materials whenever possible to control and carefully manage the radiative emission, not only rate but also angle, and to fully utilize the entire spectrum. Of course, we have to do this at low cost, which means large area nanostructure fabrication with low cost. But if we're able to do this, this will put us in a very good position to be able to generate electricity at grid parity at unsubsidized costs. And that will be the real pathway to true energy supply significance for photovoltaics. So thanks very much.
Are there any questions? We have an online question.
So the general questions online were related to the commercial viability of these complex structures, so the plasmonic light trapping,
right.
the narrowing the emission angle, and the spectral splitting. So to take plasmonics for an example, they can increase in efficiency by combining with thin film solar cells like SIGs and
yes.
CZTS. But the plasmonic material itself is made from a noble metal. So
yeah. Okay.
how could you reduce the
right.
cost of the gold or the silver structure?
Yeah. Well, cost is always a very important factor in photovoltaics, and in fact is making it, driving the challenges that I talked about. But certainly for all of the designs that I showed that involved plasmonic structures, one can achieve, in many cases, comparable performance by using non-noble metals like copper and aluminum. Actually, some nice work from the work of Vivian Feria showed this, that the same kind of performance can be used with metals that are in widespread engineering use in photovoltaics. Let me say also that in terms of nanoscale structure fabrication, there are now emerging commercial approaches to doing nanofabrication at very large scale. For example, there's a company in the Netherlands called OMT, which is now a division of Moser Bayer, that has taken some of the nanoprinting capabilities that were developed in the compact disc industry and applied these to develop tools for fabrication at the square meter scale of nanostructures. So I think we're going to see now that nano imprint lithography and nano fabrication, nano pattern fabrication is not necessarily going to be just a laboratory curiosity, but it's really going to be potentially a manufacturable technology.
How are these interrelated? Because it seems to me that if we have to reduce the entropy going out of the system by better controlling the angle of emission, we must not be generating entropy inside, so it seems like they're coupled in some way.
I think the way to view this in thermodynamic terms is the same way we do, as an undergraduate thermodynamics, is to sort of draw a box around your subsystem, which in this case is the solar cell, and then look at the entropy of the light going in and look at the entropy of the light going out. And indeed, there's internal randomization of light due to scattering inside the solar cell and spontaneous emission. But it's really that flux balance that we're looking at in doing the analysis. So you can think about that in terms of an equivalent photocurrent, an equivalent dark current in the solar cell.